All right. So we're going to start off with the video, like what the model actually does. So here's a short video. So first off, in robotics, there are two ways of building an internal representation of a net. It can be a metric or a topological. So the metric framework or the metric map is the most common for humans and considers a two-dimensional space in which it places the object. And the objects are placed with precise coordinates. This representation is very useful, but it is sensitive to noise and it is difficult to calculate the distances precisely. But in the topological framework, which the authors used in this paper, it only considers places and relations between them. So no metric information, no distance information. So distances between places are stored. The map is then a graph in which the nodes corresponds to places and the arcs, edges corresponds to the paths. So a little short introduction. So at each time step t, we get an observation OT, and then we have an action AT from our action space, which are these we see at the bottom, like do nothing, move forward, move backward, move left, move right, turn left or turn right. So we have 7 actions. As we also saw in the video. So we have actually 2 stages. One is learning and the other one is goal-directed navigation, as we also saw in the video. So in learning, the agent builds an internal representation of the map given the video footage, and then it builds the internal representation. And in the second stage, the agent uses this representation to reach the goal. So this goal-directed navigation is performed in an episodic setup, with each episode lasting for a fixed maximum number of time steps, basically 10,000 time steps, or until the goal is reached. So let's talk about the model itself. So this is a general overview of the whole model, Sptm. So given the current observation O and the goal observation OG, Sptm generates a waypoint observation, OW, which lies on a path to the goal and can be easily reached from the agent's current location. So the current observation and the waypoint observation are then provided to a locomotion network, which is responsible for short-term, short-range navigation. The locomotion network then guides the agent towards the waypoint, and the loop repeats. So at the end, hopefully, we reach our goal. So what is waypoint? It is basically a short-term goal. But actually, Sptm consists of 2 components. Here we call it retrieval network, or short in R, and a memory graph G, and the locomotion network L. So Sptm consists of these 2, and then on top of Sptm, we have another one. So R and L, 2 convolutional neural networks, and they are trained in a self-supervised fashion. We're going to talk about those in detail. So let's start with this R.
And the question is about dimensionality of input. So this O, current observation, it is an image, right?
Yes.
And OW, waypoint observation, it is a vector of dimension 512.
That is correct, yes.
So how do you concatenate the current observation O and waypoint observation OW, which you put in together into the green locomotion network?
Yes. So these all are observations, like all of the observations, they're in 512 dimensional vector space. So we give, this is 512 dimension, and this is also 512 dimension. We concatenate them. So in total, we have 512 times 2 dimensions, so 1024. And then this is the input for the locomotion network L. So we concatenate these two, and then we have 1024 dimensional vector, which goes to this network, and then this network predicts an action. So each of the 2 input observations, these 2 of them, are first processed by a deep convolutional encoder, which we see here, based on ResNet. This is the full ResNet. So in ResNet, we were given an image, and then we do all these convolutional blocks, and then at the end, we get 512 dimensional vector, and then we pass it to a fully connected layer, and then we get the output. So what they do is they chop off this fully connected layer at the end. So whenever they put an image, they get 512 dimensional vector. And then what they do with that 512 dimensional vector is first they have two of these encoders, basically based on ResNet. So this is called CME's architecture, when they create the same architecture twice. So what they do, they put each of the images into this network. So we put OI, and then we get 512 dimensional vector out of it. And we do the same for OJ. We put it in the, again, ResNet 18 based encoder, and then we encoded our observations here. Then we concatenate these 2. So in total, we have 512 times 2. And then they pass this to a fully connected layer, which consists of like 5 layers, 5 fully connected layer. Each of them have 512 units, and with Rayleigh activation function. And out comes two-way softmax, so whether they are closed or not. So out comes a probability of +0 and 1. So what R does is basically it estimates whether a given 2 observations, O1 and O2, are temporally closed or not. So basically it estimates the similarity of the 2 observations. The network is trained to assign high similarity to these 2 observations if they are temporally close, and low similarity if they are temporally distant. So they cast this as a classification task, whether these 2 observations are temporally close or not. So to generate the training data, a random agent explores the environment, resulting in a sequence of observations, here we see, and then actions. So from those, they generate training samples. And each training sample is then a triple, 2 observations, and a binary variable y, yij. And yij is 1 if and only if these 2 observations are separated by at most 20 time steps. And then these 2 observations are further away, which is, or in other words, yij is equal to 0, if and only if these 2 observations are separated by at least m times l time steps. So these m and l are hyperparameters, and then they choose l to be 20, and then they choose m to be 5. So here what we can see is that, for example, let's say we are at the observation I, let the I be equal to 10 and j be equal to 11. Okay, so we have observation 11 and observation 12. So these are going to be close to each other. So yij, y10, 11 will be 1 because 10 minus 11 is within this range. So, and it makes sense. So two consecutive observations, we expect them to be close to each other because, they look, because they are similar. So this is the idea. And then 2 observations are considered, they are farther apart from each other if the distance, I'm saying distance, but don't get me wrong. And they're considered as farther. So let's consider, like, again, I and j. let's say that I is 10 and then J is 110. So imagine, M times L is 100 here. So 10 and 110. So the difference is like 100, so that makes sense. So then they're going to be observation 10 and observation 100 will be 0 here. So they will be farther away. So within this two things, like between 20 and 100, they're not doing anything. So they think that it might confuse the algorithm.
So
yes.
Just to remind, the training was done via video observation. And in video observation, you have a sequence of images. And then we train the categorizer to detect whether two random images from the video are close together or far away. And that's what is represented here by retrieval network. The convolution is done by ResNet, and this retrieval network is just 5 fully connected layers which do categorization of concatenation of two vectors which represent two images. A retrieval network has several functionalities in this architecture. When the graph of vertices is provided, retrieval network allows to localize in the graph vertices which correspond to the current observation and the goal observation. So how can we do that? A naive approach would be to use retrieval network to calculate similarity values between provided observation and every other vertices in the graph. And the pair with the highest similarity value would then indicate localization. However, such a naive approach is susceptible for perceptual aliasing because it can be not trivial to distinguish between different locations with the same visual appearance. Therefore, in the paper, authors proposed to retrieve agent's location as the median of 5 nearest neighbors of the observation in the memory. Another modification is to perform the nearest neighbor search only in the local neighborhood of the previous agent's location, and the global search in the whole memory only if this initial search fails. This is allowing for temporally consistent self-localization, and it is also reducing the search time. The second functionality of the retrieval network is loop closure. It is necessary because at the beginning the graph is populated by exploration sequence provided to the agent, and the resulting graph is just a long chain of vertices. In order to make additional edges in the graph between not neighboring vertices, agent needs to use retrieval network to measure similarity values between all vertices in the graph and connect by an edge those which are the most similar. However, there is one restriction to avoid a lot of trivial connections of vertices which are temporarily close to each other. For example, vertices 1 and 3 are not connected by an edge, but the retrieval network may classify them as visually very similar and therefore may try to connect them by the edge. In order to avoid overpopulating of the graph with such not very informative edges, two vertices have to be separated by at least 20 time steps to be eligible for an edge connection.
So here we have observation VI and observation VJ. So again, they take some sequences of observations. So they go 5. This is delta TW is another hyperparameter, and they try different parameters. And so this is 5. Okay. So what they do is they go 5 step back, 5 observation back, and then they compare these two. And then they go 4 steps back, they got the probability. They go 3 steps back, they got a probability. They go 2 steps back, 1 step back, and then they get the probability of observation VI, observation VJ. And then they go further, they go 5 steps more. So observation VI plus 1 and observation VJ plus 1. And they get the probability. And then they continue to observation VI plus 5 and observation VJ plus 5. So what they do here is we get, instead of 1 probability, we get 10 probabilities. and then they take the median of this, and then they say that, okay, if this median is higher than our threshold, then we connect these two edges. So maybe we can think of this as, let's say we are here, this is observation VI, and then let's say this is observation VJ. So let's say that it might happen that our R, network R, can predict can assign a high value for this similarity. Okay, so let's say these two. Well, in fact, these are not really close, right? So they're farther apart. So in order to avoid this problem, that's why they do this. So what they do again, so this is our observation VI, observation VJ. What they do is they go 5 steps back. Let's say these. Let's say this is, we went back 1 step, and then they go back 1 step here too, and then they compare these ones. And then they get a probability for these two. And then they go 1 step back, they calculate the probability for it, and then let's go 1 step back from here, and they calculate the probability for these two. Again, they not only go back, they also go further. Let's say we went here, and then we went here. And then they compare these two probabilities. And then they take the median of all those probabilities. Then that is, they connect these two vertices.
And also, one more comment is that it's necessary or it's useful, for example, if its agent is turning around and walls may have the same texture. Whenever the agent turns around and see an image of the wall, then if we use only comparison of 2 images, then
exactly.
Each turn will be, in any place in the maze, will be a loop closure.
Exactly.
And actually, if you take a look into the maze, if you go at the very beginning at the video, each wall texture quite unique. So you can barely find the same wall texture.
Exactly.
So all of them are unique. If we have like a normal walls, in a normal shooter, most of the time walls have the same texture, so probably it will not work in a such environment where walls are not unique.
Exactly, that's correct. So this was one additional point I wanted to discuss at the end, actually. So it's about the textures. The authors tried it on some other environments with different textures, and then they got the results, and it's basically lower than what they got in here. So the textures pretty much are unique here. So that's why it kind of works in here. But yeah, I'll discuss it at the end too. So let's say that we know where we have our graph, and then we know where we are. So let's imagine that we are here. Our current observation O, it's here. We're here, and then this is our goal observation. And then they do planning from this. So how can we go from this point to this point? So current observation to our goal. Like which path should we take? So they do this step here, the planning part, and they use. Let me put you here. Dijkgraaf. I don't know how to pronounce this, but they use this algorithm. So thanks to the graph architecture or the graph library they use, they are able to calculate this planning step. So they calculate what is the shortest path. So they can calculate this. So you can say that, okay, how can we know these two are similar, or why don't we go this way and this way? So this is thanks to how the graph is the graph, basically. So they have all these informations, like which time step we got this, which time step we got this, and then that's how they calculate it. And then after we know that our planning, what the shortest path is, then they do the waypoint selection, basically the shortest goal, short-term goal. So we can say that each node in the shortest path, so here each node in this shortest path will be a waypoint, basically. So let's say we're here, and then the next waypoint will be this, and then when we're here, the next waypoint will be this, and then this, and then this. We can say we can do it like this, but let's call it like this. So vertex is 0 in the shortest path. So let this be equal to this one. And then vertex 1 in the shortest path, it is this. Vertex 2, and then it goes to up to vertex n, which is this, our goal. So again, here is the notation. Vertex 0 in the shortest path is where we are right now, vertex A, where the agent is. And then the last one is the goal. So we can do this, but this can lead to selecting a waypoint that is either too close, let's say these, or maybe too far, so not reachable. So therefore, they follow a more robust adaptive strategy where they say that, okay, our waypoint vertex should be the vertex L, the one of these in the shortest path. And then they calculate L, or they calculate L with this formula, where they try to maximize I such that this condition holds. Okay, what is this condition? It's basically the observation where we are here, and then the observation of VI in the shortest path. Okay, so let's visualize this. So let's say we are here again. And then what is I? I will be this next one. So we basically take this observation and then this observation, and then we give it to our network R. And then we look for if it is higher than a threshold again. And then if it is higher, okay, that's good. And then what we do is we go for another I. So let's say the second one, we increment it by 1. And then in this case, what we do, we compare this observation and this observation, and then our R spits another prediction. And then if it's higher, then we take that I. Why? Because we're trying to maximize I. And so how many I's do we have? Like how many vertices do we go? This is also, again, a fixed window. They set it, another hyperparameter. But this is basically from 1 to 7. So they only look further 7 vertices. And then they choose the I within this range, like 1 or 7, which gives a higher threshold than this, and then the maximum I. They take this. Okay, again, so instead of doing this, so for example, going from this and then this one and this and then this, what they do is they basically skip this, and then they directly give this as a waypoint observation from this point. Okay, so this is how they navigate. So lastly, out of Sptm, they have this Locomotion Network. And what this does is basically it maps a pair of observations which are current observation and the goal observation into action probabilities. L is also trained in self-supervised manner, so based on trajectories of a randomly acting agent. So when we will let a random agent, and then we get the observations and then the actions, and then they generate the training samples from these trajectories by taking a pair of observations, like I and J, separated again at most 20 time steps. And then they take the action corresponding to the first observation, so action I. That this is our training data, observation I and J, where I minus J is at most 20, and then we get the action from the first observation. Just let the agent explore, let's say, the environment, and we get our observations and the actions corresponding to those. Well, let's think like I10 and J30. So there might be a difference, but again, if it takes like half a second, then there might be a real difference. So they take a random action, and then they take the same action 4 times. So yeah, I forgot to say that. So we put these 2 observations into, again, an encoder based on ResNet, and then out we get 512 dimensional vectors again. We concatenate them again, and then we put it to a single fully connected layer, and then out we get 7 output, which corresponds to our action space. And so this is basically how it works. So this is where we are right now, where the agent is. And then this is our goal, the goal that we want to reach. and then this is the waypoint selection. So in the video, we can see we see that too. So this is our goal, the final goal we want to reach, and then the waypoint is created, and so the agent is trying to get this observation. So basically, which is at this here at the corner.
How it should be better to say? I suppose the waypoint is not created, but is selected from what was already seen before.
That's right. Yeah. Sorry. Let me rephrase. We do not create it. We just select it.
So we store in memory all observations as 512-dimensional representations, and then we connect them into a graph, and then we select waypoints.
Exactly, yeah. So we store all those nodes, so 512-dimensional vectors. And this is the training maze, only one. And then they tested on 7 different mazes. And here is the result they got. So the red one is theirs for each test set. And then these are the other benchmarks that they tested on. So here we say that like 100%. So what this means is basically in all of the test cases, they find the goal observation. They reach to the goal observation. So they cut this in 10K steps. So they basically put a threshold for this number of episodes, as also mentioned in the beginning. So it's either 10,000 steps or 2.5 minutes. Again, it's another number. So one of the review was like, why 2.5 minutes? Maybe we should give more minutes for these algorithms for the other benchmarks. But again, they put a threshold like this. So they only consider an evaluation is successful if they reach the point with below 2.5 minutes. And so here what we see is a walkthrough trajectory here on the left, and then 3 goal-directed navigation tasks. Okay, and so in the walkthrough trajectory, the shortcuts automatically found in the Sptm graph are shown in red. So these red ones are what the Sptm found in the graph. And then the goal-directed navigation trials shown track 1, 2, and 3 were all successful, as we can see. So green is where we start, and this is our goal. It reaches, and it's the same case here. In the third one, it also reaches, but it takes a pretty long time. So we can maybe explain this. Maybe it does some loops over here or here. We can see that. So maybe it was confused because of the textures. Maybe it found some textures pretty close and then took the action, but it was wrong. So which led the agent to do some loops. Maybe that's possible. But at the end, it found the point, the goal. Some additional info. So goal localization is only performed once in the beginning of the navigation episode. So we only calculate this once, like our goal. And then shortest path to the goal from all vertices of the graph also computed once in the beginning of the navigation. Another point is resolution of images are 160 and 120 pixels. This is pretty high. They also mentioned this. This is the highest resolution they have in academia, and that's why they use like ResNet, so pretty heavy network too. And they use mini-batch size of 64 and Adam optimizer with learning rate and momentum data like this. And then they trained R for 1 million epochs, and then L for 2 million epochs. So they tried, again, Sptm on different environments, but the score dropped quite high. I will show in here. So, for example, they tested in some other environments with some different textures. Here are the environment names. And then this is the score they got. So remember that at the beginning, they got 100%. So they reached the goal observation in all the cases. But here we can see that the accuracies got pretty low. But the other best RL-based baselines, they are worse than this algorithm. We can also see that. So it does better job than the other RL-based baselines. Another thing was that the problem, like Andrew, you mentioned, like a model cannot distinguish two identical frames. That's true, and they also say it in here. Okay. Okay. Anyways, so they say that the model cannot distinguish two identical frames. So that's the problem. So I put a few questions here. So each node has 512 vectors. Yes, each node has a 512 dimensional vector, and they are all stored in the memory. So we have, like, let's say, extreme use cases as to why we use median for the creating node. So again, like I explained, so this is good for we're not only depending on two observations, but a sequence of them. So that is why. So for a 5-minute video, that means like approximately like 9,000 nodes, or maybe more than that. No, they set this threshold very conservatively, and then they make sure that they only create 2,000 nodes. So again, how do they cut these number of nodes? So by selecting a consecutive threshold. So here they tried some other number of shortcut values. So here at the beginning it was 2,000, but they tried it with 1,000, 4,000, and then 8,000. And these are some threshold values that we saw, but like for localizing, and then for another threshold. And then this is the score they got. Again, they report the percentage of the success if the trials are successfully completed in 5,000 steps. So again, they do it like this. So they limit the number of steps to be taken. Yeah, well, this is pretty much it. Are there any questions?